Hello everybody and welcome to this video on coroutines. Coroutines are functions that allow execution to be paused at some point in time and then resumed from that same point later on. When dealing with the execution of two traditional functions, the first function would be executed in full, then after it is complete, the second function would execute. Coroutines are functions, but they work slightly differently. In this example, the first coroutine would begin executing. It would then pause and pass control to the second coroutine, which might, for example, execute in full. Then once complete, it would pass control back to the first coroutine. So control would be passed back to this point in the first coroutine. When the first coroutine begins executing again, it's already made progress to this point, so it doesn't need to start from the beginning. This saves time compared to traditional functions and is why coroutines could be used in cooperative multitasking. Coroutines are useful for input/output bound operations, so operations that require waiting for data, for example. There is therefore a variety of applications which coroutines can be used in. They could be used on a web server that needs to handle many incoming HTTP requests at the same time. Similarly, if you were designing some application that needed to get data from some external source like a web server, then this could utilize coroutines. Also in video game graphics, they could be used in splitting different pieces of computation into a predetermined time span to maintain a consistent frame rate. So there's many different applications they could be used in. In this video, I'm going to be focusing specifically on coroutines in the Python programming language. There's a number of key events in Python that had an impact on coroutines. The yield from keyword was introduced in Python 3.3, which allowed the delegation of control from one generator to another. A generator is a routine that returns an iterator. Before Python 3.3, a generator could be used in a coroutine-like manner, but when yield from was introduced, you could delegate part of a generator's operations to another generator, which made it easier to manage asynchronous programming. The async IO library was then introduced in Python 3.4 for writing asynchronous code in Python. Generator-based coroutines were still being used, but Python now had a standard pluggable event loop model. The big change was in Python 3.5. Coroutines could now be defined using the async def syntax, and await expressions could be used inside of coroutines. Now let's have a look at how coroutines are implemented in Python. In these code examples, I'll be utilizing the async IO library that we mentioned previously. It will allow us to handle multiple tasks concurrently, but for now, this is how we define a single coroutine. It's the same syntax as a subroutine, but with the async keyword, defining that the function could be run asynchronously. Here we're just printing a message inside the coroutine to check we're running it correctly. If we were to call this coroutine like a usual function, it would return a coroutine object, so it's slightly different in how it works. Instead, we have to create an event loop using this run method. An event loop runs and manages coroutines and tasks, deciding which has control at any given point in time. In this case, we just have one coroutine. Unlike a traditional subroutine, the coroutine will return a coroutine object, and then the run function will await the coroutine. So that means it retrieves the object and executes it inside the event loop. If we were to run this code, we can see that it prints the message as expected. As we mentioned before, one of the main features of a coroutine is that it can pause its execution. This can be done using the await keyword. The async IO library then has its own version of time.sleep. This sleep method is non-blocking, meaning other tasks can run whilst that coroutine is waiting. You can see if we run the code, it will wait for 2 seconds and then resume its execution. What happens if we have multiple coroutines? Well, we define them as we did before. Instead of like a traditional function where one runs and then after the first one is finished, the second one runs, we can use the gather method to run these coroutines together. You can see this in action here. First coroutine executes and then the second coroutine executes. This is more efficient, as if we were to run the code, we can see the total runtime is less than 3 seconds. So when the gather method starts its work, it schedules both coroutines. The run method then starts the event loop, which will then pick a coroutine to run first. that coroutine will then hit and await and pass control to the other coroutine. This then continues until both are executed. So the gather method allowed us to run multiple coroutines together. It completes when all coroutines are finished executing, but maybe we want more control to manage each function individually. We can do this by wrapping a coroutine into a task. When we do this, that task will immediately start running. We can then use await to wait for that task completion. So we can do this individually for each task. This gives us more flexibility. We could, for example, then catch what happens if a certain task was to fail. But if we execute the code, we will see it will be producing the same result, but this time we've defined the two tasks separately. Finally, let's look at an example of how coroutines could be used when making HTTP requests to APIs. We're calling two different APIs in this example, one that returns information about a user and the other that returns facts about cats. We use the AIO HTTP library here to allow us to make asynchronous requests. We create one session object which we use for both requests. We then use gather so both URLs can be fetched asynchronously. The fetch URL function here at the top returns the JSON response in this case when it is ready. So if we run the code, we can see that we get information about the user and we also get a fact about cats. Overall, we're speeding up execution because while one task is waiting for a result to come back in response to the request, the other task can begin to send its request. So that was a look at coroutines in Python. Thank you for watching.